Okay, so today our topic is lower bound theory. So till now we have uh, studied about the finding the time complexity of an algorithm, the asymptotic notations, and uh, different bounds. Okay. Next, there we have already told about the best case, worst case, and the average case time complexity, and also the upper bound, lower bound. Okay. So here that means I can expect that already you are having some knowledge of what is upper bound, what is lower bound, and all these things. Okay, best case, worst case, like that. So, what is the meaning of lower bound? Lower bound means that at least we require this much of time to execute the algorithm. Okay, or the minimum uh, time required to execute the algorithm. That we can say that this is the lower bound. But please should not confuse with the lower bound and the worst case time complexity or best case time complexity. Okay, lower bound means the minimum time required to execute an algorithm. That may be for best case, that may be for worst case, that may be for some other cases. Okay, like average or something. Average actually does not comes under this, but we can say that lower bound means the minimum time required to execute the algorithm. It may be for best case, it may be for worst case also. Okay. So we know that the omega, already we have studied Fn equals to omega, big omega of, not only omega, big omega of g of n. That implies Fn equals to big omega of g of n implies that Gn, just for recapitulation, Gn is the lower bound for f of n. That already we have studied. Okay. So this represents the lower bound for the given function fn, and Gn is the bound, right? Now, so that means we require minimum amount which is represented by a function of n Gn to execute or an algorithm whose type complexity is given by the polynomial f of n. Next, though it is looking at what is there in finding lower bound, the problem is that suppose I want to derive an algorithm, or I have already derived an algorithm, let A, and someone has derived an algorithm, say B. Now, how to compare that which one is best among these two? Okay, so in best case we may not be able to find the difficulties, because in some cases best case may give you a constant time, in some cases best case may give some greater than this. But whenever we have to found the lower bound, that means minimum time required to execute this A for a given set of input size, and the minimum time required to execute B for a same set of input size. So by comparing these two bounds, we can say that which one is best. So lower bound is very very important for finding the best or better algorithm. Here, the thing is that deriving good lower bound is more difficult than deriving efficient algorithm. Okay, I think already we have discussed some examples on that. So you can find an algorithm which can solve a problem P, but to decrease the lower bound for A, that is the minimum time required to execute this A, is a very challenging job. Okay, so therefore it is not impossible, but it is a very difficult job to find a good lower bound algorithm. Okay, right. Uh, so therefore we require to go for finding a good lower algorithm which is having better lower bound than the existing one. So that's why we require to find the lower bound of an algorithm. Next, suppose an example that what is the difference between upper and lower bound here. If we have to find the maximum of n elements, Suppose n number of elements are given, and we have to find the max among all these numbers. So we know that for I equals to 2 to n, something like that, we will check if is greater than ai is greater than max, then we will say that max equals to ai. We know the algorithm. Now the question is that what is the number of comparison that we require? Here lies the difference between best case and worst case. Okay, so whatever we are considering, we will not go for best case, because in an when the input is random in nature, so that means in worst case, what will be the minimum time required to execute the algorithm? We are not talking about the best case situation. Okay, we are talking about the worst case situation, and what is the minimum time required to execute, that is lower bound. Here in this case, we require maximum n minus 1 number of comparison, because we have to check each and every elements here from A2 with A1, A3 with next, A3, A4 and A5 and so on. So at most we require n minus 1 number of comparison. So we can say the upper bound is n minus 1. Okay, as per our previous definitions and others, we can say that n minus 1 is the upper bound for the algorithm to find the maximum among n elements. Now what is the lower bound? Here you see again, we require n minus 1 number of comparison, or minimum n minus 1 number of comparison to find the maximum among n elements. Okay, so see, the n minus 1 is the upper bound for this case, n minus 1 is the lower bound for this case. So what we can say, that there is no gap between upper and lower bound, but always it may not be true. Okay, so there lies the difficulties. So in this particular case, hope you have understood what is upper bound and what is lower bound. Okay, right. So then let us check for matrix multiplication. All of we know that to multiply two n cross n matrices, we require n cube time complexity, order of n cube. If we go for general multiplication, that is general matrix multiplication algorithm. Those who are aware about the Strassens, STRASSENS. Those who are aware about the Strassens matrix multiplications, they know that the time complexity is order of n to the power 2.81. There is another algorithm where the time complexity to multiply two n cross n matrices is 2 n to the power 2.79. So what we can write, that for matrix multiplication, the best known algorithm is order of n to the power 2 plus epsilon. That epsilon may be equals to 1 or less than 1. Okay. So we cannot conclude that the lower bound of matrix multiplication algorithm is a fixed value, that is n to the power 2.81 or n to the power 2.79 or something. We can say that the time complexity or the lower bound for matrix multiplication is or can be written as order of n to the power 2 plus epsilon. So if you decrease the value of epsilon, that will be the best algorithm. So always we have a query that is there any better method? So that's why we always try to search or to try to find an algorithm to multiply two matrices where the time complexity is order of n to the power 2 plus epsilon, and where epsilon is less than 0.79. As till now, as per my knowledge, this is the best algorithm, n to the power 2.79. But most common and popular algorithm is this one, Strassens, which is taking n to the power 2.81 like that. Okay. So always our target will be to find an algorithm with better lower bound. Clear? So that's why we require to learn the lower bound theory. Next, for this, to compare between two algorithms by using lower bounds, or to compare the lower bounds of two algorithms, we will use a technique or the method which is known as comparison trees. Okay, we will use the method of comparison trees. So where, and this is useful for finding lower bounds for searching and sorting algorithms. Later I will discuss that why it is known as comparison tree and why you should go, why I have given the name this comparison. And you will find that searching, sorting all are depending upon a particular theory or method. That's why we are saying that it is a comparison tree. Okay. So comparison tree is a useful method for finding lower bounds for searching and sorting algorithms. There are some other methods, but these are beyond our syllabus, so that's why we will only discuss the lower bound theory for finding the searching and sorting algorithms. Okay, right. Now, how to find or how to derive the lower bound for sorting algorithm? Let us check. What is the sorting? Sorting is nothing but a given set of distinct values. We are considering distinct values. You can say that, sir, why not duplicate values? Yes, you can. But for the sake of simplicity, I am considering the distinct values. Okay. So we are given a set of S distinct values on which an ordered relation less than holds. Think about that. If we are having a sorted list like that, 5, 6, 9, 11, 14, 16, like that, you say this is a given set. Okay, a set is there, set of numbers where this less than rule is applied. So all these ordered sets, this is the ordered set where the relation less than holds, and that is sorting. Okay. So in other sense, we can say that we are comparing these two elements and finding a relationship between these two. If we have to go for ascending order, just we have to find that whether this relation holds or not. Otherwise, we have to do something. In another way, think about that. Suppose we are having a list 5, 9, say 6, 14, 11 and 16. If we have to go for finding a sorted list, what is our target? There are n number of, if there are n number of elements, then we have factorial n number of different permutations of all these elements, right? If we are having n number of elements in a list, we have factorial n number of permutations of all these elements. Now, among these, only one will follow this rule where less than relation holds, and that is 5, 6, 9, 11, 14, 11, 14 and 16. So this is the particular permutations of the elements where this less than holds. So what we can say, sorting an element is nothing but calls for determining a particular permutation, nothing else. Okay. So sorting means we call for determining a particular permutation where this ordered relation may be less than or may be greater than holds. So searching and merging, both the algorithm work on the same ordered relation. So if we have to search an element and if we have to merge some elements for sorting or to get the sorted list, then we work on the same ordered relation. Okay. So our main target is to find this. Or main target, what we can say, is comparing two elements. Here the all works. Think about, all of you are aware about the sorting technology. So all the work that we do solely by comparison between two elements or more than two elements. Okay, that is a couple of elements. So first, or group of elements, whatever we can say. So the whole algorithm based on comparison between the elements. No arithmetic involved. In sorting, we are not allowed for any arithmetic calculation. Moving elements is permissible. So, in sorting, what we do, we compare the elements. We do not go for any arithmetic calculations, but we can swap. That means we can move the position of the elements. That is sorting, which is allowed. These kinds of algorithms where the whole algorithm is based only on comparison or comparing between the comparison between the elements, these kinds of algorithms are referred as comparison based algorithms. Okay? So searching and sorting, which are depends on comparison, are known as comparison based algorithms. Clear? Right. But counting sort, I think you have the idea that what is counting sort, what is radix sort, and like that bucket sort. All these sorting are excluded from this comparison based algorithm list. So these are not comparison based. Okay. Here we use some other techniques to sort the elements. So therefore we are talking about the algorithms where the whole algorithm is based only on the comparison between the elements, and these are known as comparison based algorithms. Before going to the sorting, let us first try to find the lower bound for the searching, okay, ordered searching. So again, we are using the comparison based algorithm. Already you have defined that a comparison based algorithm is that where every comparison between two elements of the set is of type compare X with AI. Think about any searching algorithm. What we do, we generally try, actually the problem is that find whether X is present in the list or not. So what we do, we compare X with A1, then A2, then A3 and so on, right? So each and every step is following compare X with AI. I varies from 1 to n or something like that. Okay. In any kind of indices you can use. Next, the process, this process, that is, this searching process can be described by a binary tree. Okay. What type of binary tree? Where internal nodes represents comparison between X and AI. So if we want to represent a comparison tree for searching, then we can say that internal or the process AI or something like that can be represented by a internal node where each internal node represents comparison between X with an element AI. Now, if we compare X with AI, what we will get? Either X is equal to AI, or X is less than AI, or X is greater than AI. These three possibilities are there, okay? Only these possibilities are there. So we can consider that if X is less than AI, we can say it will go to the left branch. If X is greater than AI, it will go to the right branch, okay? And if X equals to AI, this is the internal node, and then we will say that this is successful. But here, our target is to go for finding the lower bound, that is the minimum number of steps required when we are having the random element. So, unsuccessful, okay. So, worst case, the time complexity minimum time required in case of worst case. So, here we are having three outcomes, this one less than AI, greater than AI, okay. Now, if an algorithm terminates, think about, later I will give one example. If the algorithm terminates by following either left or right branch, we can say, later I am showing an example. Just think about that. If the algorithm terminates by following left or right branch, but before another comparison, that means suppose we are comparing A with A1, okay, and up to that x equals to an, and n is the maximum element. So the list is 1 to n. I have compared x with an. After that, if this search is unsuccessful, what will be there? It will go to the left branch or right branch or whatever, anything, any branch. So there is no other element to search with x. Think about that. If the algorithm terminates by following left or right branch, but before another comparison between x and y, x and an element of ai. So before comparing x with the next element which does not exist, then what we can say, it has gone to the leaf node, okay, and the algorithm terminates without finding the element in the list. So what we can say, that algorithm should declare that the algorithm is unsuccessful or the search is unsuccessful. Not the algorithm is unsuccessful, the searching is unsuccessful. Okay. So if we follow this to draw the comparison tree of searching, then we can find the lower bound for the searching algorithm. So let us check. First we will consider one linear search, and after that we will consider a binary search. So in linear search, what we do, generally we start with x is equals to a1 or not. So this is an internal node, okay. So already we have discussed that we will compare x with the element a1, then a2 and so on. So this is an internal node. If this is not equals to a1, then we will get a failure, okay. If there are more than one element, then what we will do, we will check the list with a2. So this is the internal node where x is being compared with the next element. If this is not equals to a2, then we will get failure, and if there is more than two elements, then we will get x equals to a3 and so on, okay. We have to compare. So these are the internal nodes represented in linear search, and if we go on this way, what we will get, x is being compared with an, and this is failure and this is also failure, okay. Now think about that. If the algorithm is searching the first one, second, third and the nth, and if this is not true, then what we will get, either we will get this failure or we will get this failure. That means we have stopped, terminated. Therefore we can say that if we reach to this leaf node, this is an unsuccessful search, and the comparison tree of linear search can be represented in this way, okay. Let us check for the comparison tree of binary search. We know that the in a binary search, first the element, so here in this case, generality, we are considering that the mid value is n plus 1 by 2, okay. So we have considered 1 to n. So first we will the element with the mid element of the list, and after that what we will do, we will check the list or the element with next half. So we can say that this is n plus 1 by 4, and here also x will be checked with the next list of the elements, that is x of a 3n plus 1 by 4, like this, okay. Just we check this value. Then in this way, if we go on searching the list, So what we will get? Ultimately, we will get x is compared with a1 and dot dot. You can go to this subarray or the subtree where x will be compared with the list. Sorry, you can give. We are talking about the array, so let it start. So n plus 1 by 2 minus 1. You can compare this, and similarly for this one we will reach to the last node. If this is successful, then it is fine. If not, then the last leaf node is failure here. So all are the terminating values are failure and failure. So in between, in any internal node, the search is completed, then fine. Otherwise, the lower bound in worst case is we have to reach up to failure, not the success. So what is the maximum number of iterations that we require? This represented by the worst case, and the minimum time required in worst case is known as lower bound. Here our target is to reach to the failure. Here also target is the reach to the failure. So the lower bound is the time to reach from the root to the leaf node, from root to the leaf node. So a comparison tree for searching algorithm can be designed in this way. Okay. Next, let us find the time complexity or one theorem to find the lower bound for the searching algorithm. Okay. So our target is to find or prove that the lower bound for any searching algorithm is the ceiling value of log of n or log of n plus 1, you can say, which is same as log of n. Okay. Now, so before going to the proof, let us go for the statement of the theorem. So let a1 to n, let a1 to n where n greater equals to 1 contains n distinct element. Let, okay, you can go for duplicate values, there is no problem, but again for the sake of simplicity we are considering distinct values, nothing else. All the elements are ordered in such a way that a1 is less than a2 is less than an. So these are in ascending order. Okay. Now let find n be the minimum number of comparison, be the minimum number of comparison. Think about, we are finding the minimum number of comparison needed in worst case. Please be careful about all these points. Let find n be the minimum number of comparison needed in worst case by any comparison based algorithm. Okay, by any comparison based algorithm to recognize whether x belongs to A or not. Think about that. The statement is that let A is the given array where there are n distinct elements and they are following this ordered relation that all are in this order, that is in increasing order. Now we are talking about find n which is providing us the minimum number of comparison needed in worst case by any comparison based algorithm such that x belongs to A to n. Then we say that this value find n is greater equals to log of n plus 1. Sorry, the ceiling value of log of n plus 1. Okay. So here, though I have written this 5n just a general algorithm type, but this is not algorithm, this is a number only. Okay. So find n is a minimum number of comparison needed in worst case by any comparison based searching algorithm. Then find n is greater equals to log of n plus 1. So we can say that the lower bound is log of n or n plus 1. Okay, that we have to prove. Now we have to recapitulate some of your data structure theory. I don't know, most probably you have studied this. In a binary tree of depth k, okay, I am erasing this. After that, I will prove all this. In a binary tree of depth k, what is the total number of elements? I think you have studied this. The total number of elements in a binary tree of depth k is 2 to the power k minus 1. Okay, I think you have studied, or if not, then later you should tell me. So in the next class, I will show this proof that how. But I think in data structure class it should be taught. Okay. So the total number of elements, the total number of elements in a binary tree of depth k is equals to 2 to the power k minus 1. This is a theorem and we can prove this by method of induction. We can prove this theorem. Okay. There is no, this is a not big issue. So if you have not studied in the next class or before that, before the next class, you should write in the WhatsApp group. I will discuss in the next class. Okay. So, but for this class, you think about that total number of elements in a binary tree of depth k is 2 to the power k minus 1. Now, think about all possible comparison trees that model algorithms to solve the searching problem. We are having n number of comparison trees, okay, n number of or m number of comparison trees that are solving the problem of searching. Clear? The value of find n is bounded below distance of the longest path. What is this find n? Already I have told that the longest path from root, okay, to a leaf, that is the lower bound. The longest path from root to leaf, so that is minimum number of comparison required in what, that means the longest route or longest path you have to for the searching. So here find n is representing the number of nodes that goes from root to leaf node. Okay. So how many internal nodes are there? Since this is representing the internal nodes, that is x is compared with ai, and we have considered that total number of elements are n. Therefore, the number of internal nodes is equals to n, right? Okay. Then total number of internal nodes that we have to visit, okay, where the level is less or equals to k. Level means depth. So what is the total number of nodes in a binary tree of or up to the depth k, that we know is 2 to the power k minus 1. And the maximum number of nodes that we have to traverse is n, not more than n. And here the total number of internal nodes in a binary tree is 2 to the power k minus 1. So we can say that 2 to the power k minus 1 is the maximum value in a depth k. Therefore, n must be less equals to 2 to the power k minus 1. n is the total number of elements and 2 to the power k, 2 to the power k minus 1 is the total number of nodes same or at the less than the level k. Okay. So we can write n is less equals to 2 to the power k minus 1. That implies 2 to the power k is greater equals to n plus 1, right? And that implies k is greater equals to ceiling value of log of n plus 1. So therefore, depth or the height of the tree is log of n plus 1. Ceiling value of this. In general, I can say log of n plus 1. Therefore, we can say the minimum number of comparison required in worst case is log of n plus 1. Hence, the lower bound for searching is log of n or n plus 1, anything you can write. Okay. I think this is clear that why the lower bound for any searching algorithm is order of log of n. So you will not find any algorithm, you will not find any searching algorithm where the time complexity is less than log of n. This is very important, because suppose some problem is given to you, or suppose whenever you are doing a job, then you have found a problem and by mistake you did something and you have got an algorithm where the searching is less than log of n, and you have applied for patent and wrote the research paper and so many things. Then the people will laugh, because we have forgot the basic theorem that the lower bound of searching algorithm is log of n. So there will not exist any searching algorithm, obviously comparison based searching algorithm, where the time complexity is less than log of n. Okay, that's why we require the lower bound theorem, and it is very important. Okay. Now let us go for finding the lower bound for sorting. Just like searching, we will describe the sorting algorithm in a comparison based tree, or we will try to represent this in a comparison tree model, and by following this method. Let n number of elements are given, and again we are considering distinct elements, and we have to sort this. Okay. Now how we sort, or how we do the comparison? We compare the elements ai and aj, and we are having two paths. Left path is ai less than aj, and right path is ai greater than aj. So we can consider that ai is being compared with aj, and if ai is less than aj, we will go to the left path. If ai is greater than aj, then we go to the right path, nothing else. Okay. So the internal node is representing the comparison between two elements ai and aj, and this is represented only by the pair ij. So if I write ij and these two, so it is representing ai is being compared with aj, and if ai is less than j, we will go to the left side. If ai is greater than j, we will go to the right side. In this way we will go for comparing all these, and we will find the correct permutation. Okay. Next, external nodes represent the termination of the algorithm. Already we have discussed in our previous slides that external node represents the termination of the algorithm. So either it is failure, not the success, it is failure. It will be success, ai is equals to aj here. Okay. Then every path from root to an external node is a unique permutation. Already we have discussed that if ai is less than aj, we will follow this path. Then again I will compare with something. Okay, I plus 1 with j plus 1, or maybe something like that. So each internal node is comparison between two elements. External node is giving terminating conditions, and this path is giving us a particular permutation. Okay, this path is also giving us a particular permutation. If we follow this kind of path, this one is giving a particular permutation, this one is giving us another permutation. Similarly, here also giving us different paths. So again, internal nodes are providing elements, external nodes are terminating conditions, path is giving us the permutation. Okay, not any duplicate value, because we have considered the distinct values. Okay, right? Now, how many different number of permutations will be there? Factorial of n. If you count these paths, you will find that factorial n number of different paths you may get. Okay, not you may get, you should get. Now consider the worst case for all comparison based sorting algorithm. Okay, so our target is to find the time complexity, minimum number of comparison required in worst case, that is lower bound in any comparison based sorting algorithm. So let us consider that Tn be the minimum number of comparisons that are sufficient to sort n elements in worst case. Okay, so our target is to find this Tn. So what we will get? Again, we know that if all internal nodes are at level less than k, okay, there are at most 2 to the power k number of nodes, external nodes. If all internal nodes are level less than k, okay, all are up to k, say this, then we say that there are 2 to the power k number of external nodes. Why? Because at this level we can show that in this particular level, kth level, there are 2 to the power k minus 1 number of nodes in a binary tree. Okay. So in the kth level, here please don't get confused with 2 to the power k minus 1 and 2 to the power k minus 1. This is the total number of nodes up to level k. Okay, and this is representing the number of nodes at level k. So if you add 2 with each, then what you will get? 2 to the power k into 2, sorry, 2 to the power k minus 1 into 2, that is equals to 2 to the power k. So total number of external nodes is equals to 2 to the power k when we are having 2 to the power k minus 1 number of nodes at the kth level. Okay. So what we can say? K is equals to T of n, that is how many number of elements are there. Okay, then what is the total number of elements? Factorial n, because we are having factorial n number of different paths, and therefore factorial n number of external nodes must be there. So that must be this equals to 2 to the power T of n. Think about, k is the level means to reach from root to external node. Okay, to reach from external root to external node. Now if k equals to this, and this Tn is representing the minimum number of comparisons that are sufficient to sort in this worst case, therefore we can write k equals to Tn, and total number of nodes factorial n is external nodes, that is must be less equals to 2 to the power t of n. Okay. Then what we can say, that if Tn is an integer value, let us consider, obviously it will be an integer value, but we are considering this Tn is an integer value, then the lower bound we should get must be greater than log of factorial n from there. Here we have written n factorial equals to 2 to the power t of n. Okay, so t of n is equals to this. Now, by Starling approximation, all of you are aware, by Starling approximation, we can write factorial n is approximately equals to root 2 pi n to the power n plus half e to the power minus n. Okay, this can be proved. Those who are interested in mathematics, you can check this, or I think, I don't know whether it has also been taught to you in mathematics class. But for us, only this part is required, that factorial n can be approximated to this value. Now, if we take the log of this, what we'll get? Then log of factorial n is equals to, here we are considering this value first, okay, n log n plus half log n, then plus I minus log of n base e. Okay, so this is for this one, and log 2 pi is this. So we can write log of factorial n is equals to this one. Clear? And we can write like this: n log n minus log of n base e minus half log n minus log of root 2 pi. So for a large value of n, we can say that this is a positive value. Okay, and we can write that the minimum value of Tn is equals to n log n. Okay, and hence the lower bound for any sorting algorithm is omega of n log n. Obviously, any sorting algorithm means those are comparison based, not all. Like counting sort, radix sort, these are not under this category. Any comparison based algorithm, sorting algorithm. So we have proved that the lower bound for any comparison based sorting algorithm is order of n log n. So don't go for finding an comparison based sorting algorithm. Don't go for finding a comparison based sorting algorithm whose lower bound is less than n log n, because that will be wastage of your. We have proved that the lower bound cannot be less than n log n for any comparison based sorting algorithm. There, next day I will discuss a little more about this theory. But for today, if you have any query, please you can ask. Do you have any query? Anyone? Do you have any query? Anyone? Yes or no?
No, sir.
No, sir. You are Karam.
Yes, sir.
Arey Karam, what happens? No one is having any questions. So, can I feel proud that I am a very good teacher? You never have any questions, any queries. Okay, just I was joking. So I will try to send you the class notes also for at least today's class because I am not finding the previous class notes. I think I had given to your seniors and I don't know that they had returned me or not, and that is before the lockdown period. But I have this, so I will send it to your WhatsApp group. Okay. Still, if you have any query, then you can ask me in the group. Okay. So let us stop for today.
Thank you, sir.
Yeah.
Thank you, sir.